bunch of logging, and you end up having a model report. So this is an example from Salesforce where you might get a particular model that's deployed to a client, and then you have some information that's returned to them about what were the important features on that client, why did the model behave the way that it did. So that's what it means to explain your model. And then again, the question becomes, why explain the model? So this is similar to the interpretations of these questions, but there's a little bit more to it. So if you think about that data scientist who's trying to debug the model, there are a lot of things that come up. So this is an example of a plot of model performance, the F1 value on the y-axis, and then 3 different runs where you're evaluating the model. The training run, where you actually built the model, some holdout data set that you kept pure during your training to really test how the model was doing, and then the evaluation for when you deployed the model out in the wild and actually saw how it did. And what you can see is that for the red, bad configuration of this model, there was a huge drop in performance once you deployed it into the wild. Whereas for the good configuration, the performance was relatively the same, right? You got what you expected when you deployed it. And so as a data scientist, you might need to figure out why. So let's assume for a moment that this was a model of the Titanic. So I'm going to go back to the Titanic quite a lot. It's kind of the hello world of machine learning. So it ends up being a lot of my examples. If you assume that this was a model of who is going to survive the Titanic, and you saw that the top 3 features in that model were the gender of the person, the class on which they boarded the ship, and whether or not there was a body ID for that person, you might get an idea that, maybe I don't actually have body ID when I'm trying to predict things. But this is actually something that can appear in Titanic data sets, right? So people who did not survive were later given an ID for the body. And this means that you have information in your training that actually isn't there when you deploy it to production. And this is the kind of thing that comes up quite frequently with models at Salesforce. So we need to be able to detect this kind of thing. Another issue is trust. So you have to convince your clients to trust the model, to use it. And what does it mean to trust a model? It means, first of all, that if the model, a human is right about something, and the model is right about something, sort of in the same areas, then you probably say, okay, well, even if the human doesn't necessarily get this right, and the model doesn't necessarily get it right, since the human and the model are right in both cases, I can trust this model. I'm gonna go ahead and say there's no cost to giving control to the model, so it's probably all right. However, if you're in the case where the human is wrong about things that the model is right about, but the model is wrong about things that the human is right about, then maybe you don't trust the model. So if you don't have a good match between what a human can see and what the model can see, you've maybe got a problem, and you're not going to give that model your trust. In addition to trust, there's this idea of bias, right? So here is an example of a bunch of phrases in Turkish and then their English translation. So the Turkish phrases are all gender neutral. You can see if you, well, I don't know if you guys can read them from there, but the English translations are definitely not gender neutral. They're pretty much defining the things that women can do as what they could do in the 1950s, right? And so there's a very clear bias in this model that's not present in the language. And if you understand what's going on with your model, you can sort of correct for this. In this case, this is a language translation that's basically trained on the internet. And so the data that you're feeding into it is undoubtedly fairly biased, and that's reflected in the model. If you understand how that's happening, then you can start to fix it. And this comes up again with sort of the legal requirements. So there's been a lot of work. I imagine many of you probably spent some time on GDPR compliance, like making sure that everything can be erased if the person wants it to be. In addition to that, there's this idea of having to explain why particular decisions were reached. This is very common in things like the financial industry. There are acceptable and unacceptable reasons to approve or deny a loan. For instance, you can't use things like race to make those decisions. Similarly, there are a lot of things that can sort of sneak into your models that can cause problems. So I don't know if any of you saw the recent sort of New York Times story about basically models that decide, that predict the rates of recidivism among inmates. But this is a thing that's now happening in our society, right? There are models out there that are being used to decide whether or not people should get bail, what their jail sentences should be, by deciding whether or not they're likely to reoffend. And there's, when you examine these models, it actually turned out that the scores given to black and white defendants were very different. So this is in no way an equal distribution. There was further sort of studies into this that found that basically the misses on this model were very biased. So white defendants were much likely to get low scores and then reoffend, whereas black defendants were much more likely to get high scores and not reoffend. So clearly there's some bias here, and if you really understand how the model is working, then you might be able to go in and track down whatever feature it is that's contributing to it. For instance, if zip code is being a proxy for race, this might be something that you need to eliminate from your models.
Sorry, are we conflating the algorithm with the training data? Because you're referring to bias here, and the bias would be in the training data, not in the algorithm.
So the bias can be in the training data. You can also have specific features that can proxy for things that you might want to remove. So for example, a good example is the fact that zip code is often conflated with race,
right.
Which is why it's not legal to use it in financial decisions. But I don't know that there's any regulation specifically on these algorithms, so that's what the news story was about.
Okay.
So understanding the algorithm can allow you to sort of ignore the parts of the data that are leading to this bias in the model. And then the final thing that you want to do with explaining your model is give the end consumer something actionable that they can do with it. So a lot of times people just don't want just the score. They don't just want to know, all right, so this is a particular case from Salesforce, basically saying this particular sales lead is likely to convert to making a purchase, right? So this lead got a very high score. And then what we provide are the factors that led to saying that this was a high score. And so if you have these factors, you can see that it's things like the phone number being valid, the person in the score being a director, and the fact that they downloaded the white paper. And so if you see something like this, then you actually have a clue that, oh, maybe if I get people to download the white paper, I can, increase my conversions. So this is a change in business practice that's actually suggested by understanding what the model is doing. And of course, this is just a correlation, so the model is just picking up trends in the data. But what you can do is basically come up with a test, right? You can make an A/B test based on this information to say, does getting people to download the white paper actually increase the amount of conversions? And so this is giving something that allows people to improve their business practices based on having the model, so not just using the score. So hopefully I've convinced you that it's worth doing to try and explain your model. And then the question becomes, well, how do I actually go about having an explainable model? And as you might have picked up from the fact that there are all these different reasons to have an explainable model and all these sort of underlying questions that define what it means to be explainable, it's complicated. So in general, there's sort of a series of questions that you can ask yourself that will lead to different answers for what it means to have an explainable model. So these include things like, can I use a simple model? Simple models are generally more explainable. Are the features that I'm actually feeding into the model something that can be interpreted, or am I doing something crazy complicated to my features before I actually feed them into the model, such as like putting them into a vector representation of the words that gives me nothing comprehensible in my features? Is the person who's consuming the explanation actually caring about the model, or do they just care about insights into their data? Because these are very different questions that can't necessarily be answered at the same time. And finally, is the person getting that explanation caring about what the model is doing overall, or do they care about why did this particular element get this particular score from this model? Because again, those are very different styles of explanations. And so if you sort of go through all of these questions, you can come up with answers that really vary, from having things like reporting the feature weights or importance, looking at the impact of the feature in some sort of model agnostic way, or creating a secondary model for explanations. And you can do this both for global explanations and for local explanations with different techniques. So before we actually talk about what it means to implement these explanations, I want to talk a little bit about the trade-off between accuracy and interpretability. So you all may have heard that neural nets are very accurate at predicting certain things like visual recognition. However, it's also fairly common knowledge that they're not super easy to explain, right? There's not a good way to say, oh, this particular pixel was the one that really tipped the neural net to saying this was a cat, right? That's not something that comes out easily. Whereas if you have something like a decision tree, it becomes very clear. You can step through and you can say, oh, the first and most important node is what was going on here, the next node, or if you have a logistic regression, then you can get that. So there's definitely this trade-off, right? Because while a neural net might be very accurate, or a gradient boosted tree or an SVM might be very accurate, they're not explainable. However, something that's simple may not provide the best results. So a simple logistic regression may not be able to pick up all of the interactions or do the right feature engineering without very careful work. So there's definitely a trade-off between having the best and most accurate model and having a model that you can actually explain to someone. In addition to the actual model that you apply, there are earlier computations. So it turns out that there's a lot of work to go from something that might be your feature store to something that you can feed into your model. So if you imagine that this closet is your feature store, and this matrix is what you actually want to feed into your model, you can imagine that the steps to get from your feature store to your model might be many. They might cause a lot of difficulty in actually interpreting what's going on. So you can think, let's take this literally for a moment and think, all right, if you had someone textually write a description of every item of clothing in this closet, and then put that through a translation into a word-to-vec representation in order to model what was in the closet, it would be completely uninterpretable to say, oh, features X2 and X4 are the important ones, right? Even if you could get away with a very simple model. And so this is actually the case in real feature engineering too. Something like logs, something like textual data, even a lot of numeric features have to undergo a lot of steps of processing in order to get the best features to feed into any particular model. And those steps of processing can lose the information that you need in order to make your model explainable. And so this is a big problem for us at Salesforce because basically we're a B2B company. So we have to take in our customers' data and engineer it for every single customer without looking at it. So we do a lot of automatic feature engineering. And what this means is that we'll do something like this. So we'll get a list of features for a particular client. And it will look something like the email, the phone number, an age, a subject, a zip code. And from those features, we will basically examine the type of the feature. And Salesforce has a very rich type hierarchy that actually includes things like email as a type. And we will look at the distribution of the feature. And we will apply the appropriate transformations automatically for those features in order to get the vector that we feed in to the model. And what this means is that we will check if the email address is spammy. We will parse it to get the prefix in the domain. We will then pivot the top 10 most common domains and feed those all into the feature vector. Similarly, we'll do things like check whether or not the age is better represented as a continuous numeric number or binned into a categorical number. We'll do things like TF-IDF on rich text fields and join with external data sources for particular types of information. But all of this means is that there's a ton going on before we actually get to the features going into the model. And so the question of how we keep track of that is with metadata. So what we found is that basically it's very important in our automatic feature engineering to keep track of every step that went into it. So what we do is we keep track of the name of the feature that the column was made from. So in the case of email domain pivot, we would say that this is the domain, is the thing that the feature is made from. In addition to that, we keep track of the raw feature that this was done. So let's say the raw feature that was fed in was actually the company email address, right? And we also keep track of every single action that we performed on that feature. So we'll keep track of the fact that it was checked for being a valid email address. We'll keep track of the fact that it was parsed. We'll keep track of the fact that it was pivoted and have just a record of every single set of transformations applied to it. Will in addition keep track of any grouping information. So you want to know not just that this is pivoted email domain, you want to know that these are the 10 columns that correspond to the pivoted top email domains. And then finally, you want to know what the value is. So you want to know, is this particular email domain Hotmail or is it Gmail, right? And all of those things, once we have them, basically allow us to roll up the information in a way that on a basically per use case basis, we can produce something that is meaningful to the client. So once you have all of that information of sort of the provenance of the feature, this allows you to give something back to the client that they can understand. All right, so finally I'm going to talk about basically the difference between global and local interpretations. So there are two different ways of explaining your model. Essentially, you can look at what are the major effects in your model. What are the features that contribute most to determining if for instance, in the case of binary classification, if it's a yes or a no answer, right? Alternately, you can look at sort of the fine-grained detail and say, for this particular user, for this particular record, it received a score of 0.92, which is like 90% probability of yes. And going in and looking at the individual features that contributed most to that particular client can give you wildly different answers than what is going on overall, right? That particular client might be missing the features that are most contributing overall and might have completely different features. This gives you different insights, but it also sort of works differently for different types of models. So, for instance, there are some models where the global interpretation can make a lot of sense. Let's say you want to look at something like housing prices. Overall, you can say, oh yeah, the number of rooms in the house, the square footage, these are things that globally make sense. But if you want to try and explain something like a sentiment model, it can be very, very difficult given sort of the size of the English language or whatever language you're trying to explain, and all of the different permutations and commutations of words, why the model is working the way it is. But if you look at a single record, you can say, oh, that's not bad is positive, right? And you can get that basically from examining what the particular words are and explain what's going on fairly easily. So different levels of explanation work for different types of models. So I'll talk first about global models, and I'll sort of go through how these questions relate to the three different types of explanations that I will talk about. So basically, I'll talk about feature weights and importance for simple models. I'll talk about some model agnostic feature impact calculations that you can do in order to get explanations. And then I'll talk also about secondary models and how you can use them to provide explanations. So feature weights or importance are, I think, classically what people think about when they think about explaining their machine learning model. And if you've got the use case where you can get away with a simple model, and you've got sort of simple features that are being fed in that you can explain, you've sort of won the jackpot on explainability, right? So now you've got something that directly relates to how you want to explain your model. So in the case of, let's say, a linear model like logistic regression, what you can see here is that you might have a number of different features, a thing you're trying to predict, and each of those features will be given a particular weight, and that's what's fit, right? And if you've normalized your features so it doesn't look like these are actually normalized, but let's assume that you've normalized your features, what you can then do is just look at the weights and say, all right, the feature with the highest weight is the most important, right? It's very easy to interpret. It's giving you all the information about what the model is doing right off the bat. Similarly for decision trees, things you can go through and say, all right, I'm going to look at the different nodes and sort of trace the past, and I can get a good explanation. So this is, again, a Titanic model, and basically, if you are a male and you're over the age of 15, or over the age of 18, you likely died. If you are a woman and not in third class, then you probably lived, right? So there's these different paths that really explain what's going on. Of course, it's not always the case that you can get away with one of these models, right? they're often less accurate than something that's more of a black box. And so if you get into the case where you really need something that cannot be explained in this sort of simple and direct manner, you're not out of luck, right? There are still techniques that you can use to get explanations for what's going on. And sort of the simplest one of these is to go ahead and basically drop a feature, refit the model, see what the effect is on the overall accuracy of the model, right? This will give you a measure of how this feature is affecting your model. In fact, you can take this even further and do what's referred to as a permutation test. So if you think of each of these spots as a particular element or row within a column, which is a feature, if you shuffle that row and break the relationship with the label, you can measure how that feature is impacting the performance. If you do this many, many times, you'll get a distribution of the impact of this feature on your performance. And if your actual performance is way, way out there on the far side of your distribution, then you know that this is a significant effect. So unfortunately, as you may have sort of gathered from the idea of permuting this over and over again, it's a really expensive computation to do. In fact, it's so expensive if you've got a large number of features that it's actually infeasible for us to do at Salesforce. So while this technique worked great for me in grad school, it hasn't been something that I've really gotten to apply in industry. And in addition to the problem of cost, there's also issues of basically features taking each other's place. So this is if you have a lot of features in the real world, it's very common that those features will be closely related to each other. So this is what we call multicollinearity. And this is an example of housing data. So basically, you have the total number of households, the aggregate income, the employment base, the total population. And what you can see is that basically any one of these features can take each other's place. So it might be the case that as a whole, these features are the most important thing in your model. But if you basically take one away, any other feature can take its place, and so the model performance won't be impacted. Similarly, even if you have like a very simple explainable model, and you're doing something, the weights will basically take each other's place. Or if you're doing something like L1 or L2 regularization, what this will do is uniformly push down all of the weights of these features, or push some of them randomly to 0. And so what it may end up looking like is, even though these are the most predictive things about your features, they're not going to show up as the top factors, right? They're not going to show up as the highest weights, because basically they're contributing 1/4 each, right? Instead of something else that might be contributing, it's the only particular feature that's contributing. So this is a really big problem, basically with trying to explain what's going on for a lot of sort of real world problems. In particular, if you want to understand your data, then what it's saying is that there may not be a clear match between the true important features of your data and what the model is doing, because the model is sort of aggregating over the data. It's pushing down these effects. Which brings us to this idea of just computing a secondary model. So if your model isn't going to tell you about your data, why not just use a secondary model? I mean, then you can get really accurate predictions, you can get something to give your clients, everyone's happy, no one's bugging you, it's all solved, right? Unfortunately, the problem with secondary models is that they're often every bit as related as this teddy bear is to this grizzly bear, right? So your secondary model may not tell you anything about how your actual model is making predictions, and it may really just not be telling you very much in general if you've chosen the wrong one. So, for example, it's very common to use something like decision tree for a secondary model. I would argue that this is a particularly bad choice, because even though it's easily explainable, it's a greedy algorithm. It's likely to give suboptimal answers. And it's not likely to it's not necessarily even going to find the most important interaction effects because of its greedy nature, right? So similarly, logistic regressions suffer from sort of the same problems that I just described with multicollinearity, not actually explaining what's going on in the model. So one of the things that we really like at Salesforce is basically to try and find a secondary model that will at least explain the data. And so what's shown on the right here is my favorite plot that you can make in R. So this is a cross Correlogram. And basically what this is showing is the relationship between every single feature, each other, and the label, right? So what you've got here is, this is a lot of information about cars, and what you can see is, let's say that we're trying to predict essentially miles per gallon, which is the fourth element down. What you can see is that there are a lot of features that are very strongly negatively correlated with miles per gallon, such as the weight of the car, the displacement, the number of cylinders, the horsepower. But they're also very strongly correlated with each other, right? So these are things that, as a whole, go to the explanation, but may need to be grouped together and treated differently. And so this gives you a really nice view into the data, at the very least. So if you're going with a secondary model, it's nice to have something that will tell you something true about your ecosystem, even if it won't tell you exactly what's going on with the model that you're using to predict things. And so, in case you're wondering what we do at Salesforce, the answer is essentially that we throw everything like the kitchen sink at it. So we take all of the metadata about how we've done whatever feature engineering is needed in order to get the things that are actually fed into the model. We compute correlations and mutual information depending on the type of feature. We include feature weights and importance whenever possible to explain the models, and then we also include a lot of information about the feature distribution. And what this ends up looking like is basically sort of this massive JSON or case class that we compute that's talking about everything that goes into the model. And so this is an extremely abbreviated version of what this looks like for one particular feature, which is sex in the Titanic. And you can see it becomes two different features, which is whether the passenger was male or female, and we compute the correlation, mutual information, contribution, a whole bunch of other information about these particular features. And then in order to actually view it, what happens is that the consumer rolls it up into a dashboard. So in Salesforce, this is what's used to create something like this model report. If you're the data scientist, then you would create your own dashboard that basically has all of the information that you need and consider relevant to debug your model. And we do this, of course, because we're satisfying everyone with this. We have to satisfy both the data scientist and the end customer. So that's how you can go about explaining sort of global models. But in addition, there are different techniques that you can use for local explanations. So local explanations, again, I'm going to put them into three different categories. So basically, as you go through these questions, they'll lead you to different answers. But there's feature weights or importance in explanations. There's feature impact, calculated in sort of model agnostic ways. And then there's secondary models. So again, if you've got the ability to use a simple model, that's awesome. It makes it easier to explain what's going on. So again, you can sort of take your features, look at their ranges, normalize them, and use the weights. So going back to this example from a regression, basically we've got our features. We're going to pretend that they're normalized in this example and that we've got some weights. If you then take your weights and basically multiply them by the values that have also been normalized in the same way that you normalized your model, you can pick out which particular features were most important. So let's say it's X1 in this particular case. Right? And what this looks like is basically giving you a contribution of each and every individual feature to the overall score. So the element on the right is the overall score, and what you can see is that this is how much each feature contributed to giving that overall score. So it's a very clean explanation of what's going on for a particular user. If you can't get away with something that's that simple, there are a number of techniques out there that allow you to determine basically what the impact of the feature is in a model agnostic way. So this is an example of LOCO, which is leave one covariant out, which is a technique that we really like, which basically, the underlying idea is that you go through, you get your fitted, trained model, and you take your row of features, and for each feature that's fed in, you null it out. So you set it to the mean, you set it to 0, you set it to empty, whatever it means to get rid of that feature for your model, and then you rescore, and you get the difference in the score without that feature. And then you basically can rank based on the biggest change in score what the impact of that feature was. So this is nice in that it doesn't depend on what your model is. As you can imagine, basically rescoring for every single feature becomes relatively expensive. So this is similar to the permutation test in that it's not a cheap operation to do. However, it is sort of more compatible with sort of the MapReduce framework. So we do everything in Spark. It turns out this parallelizes pretty well, so you can do it on rather large data sets. Basically, as long as you can ship your model to every node, it doesn't matter. You just go ahead and do your scoring over and over again on each individual node. Make sure you've got it parallelized, and it will run. And so what this ends up looking like is something like this. So here's an example of a woman who boarded the Titanic, 3rd class, with no family, siblings, or spouses, and basically did not survive. But the model predicted with a score of 0.62 that she would. And if you want to figure out why, then Loco provided this explanation that said basically if you looked at the top features, the most important feature was that it was a woman. And then the second most important feature was that it was 3rd class, which had a slight negative effect, but this wasn't enough to really push the score to negative. So this can give you a nice feeling for why particular scores were given, and it's sort of a clever technique. In addition, there's this idea of secondary models. So there's something that's come out, I think, relatively recently called LIME. And basically the idea behind LIME is that if you need to explain something like a complex neural net, and the feature engineering that you've got put into it is totally incomprehensible to humans, you can still make a secondary model that is related to the actual model predictions by essentially doing a second batch of feature engineering with explainable features, and then taking a particular record and the records that are nearby it in score space, and fitting a local model to those records, basically the scores of those records with your new features. So you'll fit a linear regression with your new understandable features to the scores produced by your non-understandable model, and this will give you a local model of what your non-understandable model is doing. There's some evidence that this works really well, but as you might guess from the fact that I'm talking about fitting a new model for every record that you want to explain, it's pretty expensive. In fact, for us, it's so expensive that we can't do it because we need to be able to explain any record that a user happens to click on, and it's not feasible to fit a separate model for every single record. But it's kind of a cool technique if you just need a couple of explanations for particular features, and a global explanation is not going to work, and local explanations are extremely difficult. So the type of secondary model that we like is actually going back to this idea of correlation. So it's not ideal, but basically what you can do is if you have all of your features, you have their correlations with the label or with the score, what you can do is normalize those features so that they all fall into the same range, multiply that normalized value times the correlation, and then you'll get a ranking of how much that particular feature is contributing to a relationship with the particular label that you're looking for. And so what we end up doing is basically use case dependent. So it turns out that individual record insights are quite expensive, so we can't do everything like we did with the global model. What we do is we basically ask, all right, so do people in this case need to know about what's going on with the model, or do they need to know about what's going on with the data? What kind of insights are they looking for, right? And depending on that, we basically decide whether we're going to use correlation or loco. And then what we do is basically compute the relevance for each of the features that goes into the model and sort of roll that up with our metadata to give a really nice textual explanation of what's going on. So that's, for instance, how we get this explanation of the phone number is valid, right? So that's based on the original phone number feature. We did a check to see if it was valid, and so we've interpreted all of that for them. And so our clients find this really helpful, and works out in most of our use cases. So if you came here hoping that I would give you a magic bullet for explaining your models, I apologize. What I hope is that I've sort of walked you through some of the use cases and giving you ideas of when different types of explanations, different types of techniques will work, and that you can sort of refer back to this and come up with whatever is going to be the solution for you in trying to explain your model. So, thank you very much.